I'm Heather Chamberlain. I'm an Enterprise Fellow at the University of Southampton, working with the World Pop Research Group. And today I am going to be talking about some work we've done to map feasibility of social distancing within urban areas. And this is particularly focused on cities within sub-Saharan Africa. So just a brief overview, we'll have a look at some background, data sets, index development, some initial results, and then look at some next steps in future work. So social distancing is probably a term that is all part of our, it's part of most of our everyday vocabulary now, but this was a definition that came out early last year from the US CDC, which was social distancing, also called physical distancing, means keeping a safe space between yourself and other people who are not from your household. To practice social or physical distancing, stay at least 6 feet, about 2 arms length from other people who are not from your household in both indoor and outdoor spaces. And this wasn't really a term that any of us used every day until about a year ago. And we can see this if we look at Google Trends for the term social distancing or social distance. And you can see that really this peaked in March last year when everyone was wondering, what does this mean? And it's now a phrase that we're very familiar with and seems for the moment at least to be part of our everyday lives, with ample signage reminding us about the need to maintain social distance in a lot of different settings. And over the last year, there's been a lot of spatial analysis undertaken to identify factors associated with COVID risk. And these have been at a range of spatial scales. And specifically in terms of social distancing, early on in the pandemic, there was some work focusing on looking at pavement widths in New York. And this was published as an interactive map, which you can see here, or in the US term, sidewalk width. And this work has since been expanded to a range of other countries and cities, including in the UK. And some of that work was presented earlier this morning. But analyses like this are dependent on very detailed spatial data on, in this case, pavements. So those, for example, that can be available through OS Master Map. But these really are only available for limited urban areas and rarely available in developing country contexts. However, social distancing guidelines and requirements really have been issued by governments in countries throughout the world as a measure to intended to reduce COVID transmission. And so this work is focused instead on urban areas, specifically in sub-Saharan African countries, and in particular, intending to identify locations within these urban areas where social distancing is likely to be difficult, if not impossible. For example, this is a slum area called Kibera in Nairobi in Kenya, where just from looking at this image, you can see it's highly likely to be, there are going to be challenges in maintaining social distance within this setting. And there has been some work over the last year looking at a range of risk factors in such settings. There's some work that was done by Peter McElroy et al., which developed a vulnerability index for Kenya, and that was developing 2 indexes, looking at a social vulnerability index and an epidemiological vulnerability index, and a composite of the two. And that was calculated for 295 sub-counties within Kenya. So it does give some level of spatial detail, but it's not going to identify like risk locations within urban areas. So an early version of this work was completed about the middle of last year through some work we're doing on a project called GRID3, which is working in a range of countries in sub-Saharan Africa. This was work in Zambia, following a request from the Zambia National Public Health Institute, which was about trying to identify locations where social distancing might be difficult. So the initial work that we did looked at population density and building density, and used an approach to essentially calculate these values for small areas, and then classified these values just by using quartiles. And then a bivariate chloropleth approach was used to map these locations where social distancing was likely to be most difficult. And so you can see an example of the map on the right here, where the dark blue locations are those areas where social distancing is most likely to be difficult. And we can see some interesting spatial patterns looking at this map. As we can see, there are locations where building density may be high, but population density is low. For example, in this area here, and this is due to this area being a location where there are a lot of commercial buildings, and the count of population in that location is very low. And so this analysis was done just for Lusaka in response to this request. And just looking in a bit more detail, you can see it does help to identify these locations where the arrangement of buildings is likely to prove a challenge in terms of social distancing. So we can see this area highlighted on this image on the right, overlaid on satellite imagery. So as I said, this initial analysis was done just for Lusaka in Zambia, but the data that we actually used in this analysis is available more widely and across sub-Saharan Africa. So we were then considering how to scale this work up. And in doing this, there are a couple of challenges that we highlighted in terms of, first of all, defining the urban extents within which to estimate this difficulty in social distancing, a lack of consistent administrative boundaries to create for small units in which we can calculate these values. And in terms of making these values, which ultimately we've turned into an index, but making these values meaningful and comparable within and between countries. But this work also provides some opportunities in that we had access to new data sets that included continental scale building footprints, and the availability of high resolution gridded population data sets meant we were able to estimate a population density measure at high resolution. So in terms of the input data used in this work, we've used data I'll group them in two ways. So we have, first of all, data that's used for defining the spatial units, and then we have the data that's used in calculating the index variables. So firstly, in terms of defining the spatial units, we use three main sources, and we use data from GHSL, the Global Human Settlement Layer, specifically the GHS SMOD, the Settlement Model Grid, and the GHS Urban Centers Database, the UCDB. And for those of you who are not familiar with these data are available with global coverage. We then also used OpenStreetMap and extracted a range of features which we used to form small spatial units. And then we supplemented this with a data set that has been produced as part of the project that this work is part of, the Grid 3 project, just to help identify locations that were on the urban fringe to help ensure that sufficiently small units could be created in those locations. Then in terms of calculating the index variables, we've used two data sets here. We've used data on building footprints and data on population. So the building footprints data are produced by Ecopia using Maxar imagery, and this is part of a project called Digitize Africa. And we were able to access this data through the Grid 3 project. And then for the gridded population data sets, then we've used World Pop data sets that are available with global coverage as well. So just a little bit more detail here. So we've got the GHS mod and the UCDB in defining the urban extents. And then the range of OpenStreetMap data that we used were primarily roads, waterways, and railways. And these were supplemented by some additional features such as industrial areas, parks, golf courses, things like that, where the land use within a unit is likely to be quite similar. And so in relation to the arrangement of buildings and population density, that's likely to have a degree of homogeneity as well. Now, in terms of actually defining the urban spatial extent, so these are the extents within which the index, the small spatial units were created and for which the index was then calculated. We went through a process where we based this on the GHS Urban Centers database, we selected that has a true positive flag, so we selected only true positives. We then used the GHS SMOD dataset, which is shown with the purple background in the center here. And then we we selected only the classes that we were considered urban in any way. So these are the 4 classes here. And then from that, we created a binary urban-rural raster. And then we subset only spatially contiguous urban grid cells. So those were grid cells that were spatially contiguous with the urban centers from the GHS UCDB. We buffered any of these urban grid cells by 3 kilometers to ensure that sort of the areas around urban centers were included, and then created a convex hull around each of these contiguous urban areas. And you can see an example in the top right here of these convex hulls around these urban centers. On the bottom left, bottom right, you can then also just see overlaid with satellite imagery how this does capture most of the urban area. And this was done for the whole of sub-Saharan Africa, which gave about just over 1,300 urban extent polygons. On the right, we've got some examples at the top for Lusaka in Zambia. In the center, we have Kinshasa and Brazzaville. So these are 2 urban centers split by the Congo River, but as the way that we created these convex hulls, this would be 1 unit that was then split by a national administrative boundary to form 2. And then here we have Sierra Leone, so Freetown in Sierra Leone. And so in this case, the extents were also clipped to coastline to ensure that we didn't include large areas of sea, for example. And so this is the full list of the OpenStreetMap features that were then used to create these small spatial units within these urban extents. And these were intersected to then create polygons, and which had a minimum size criteria of 10,000 meters squared. And so we were aiming for small units, whilst also making sure that we complied with licensing restrictions with published outputs due to restrictions on some of the input data. And so this gave rise to some spatial units that look something like this. This is an example from Lusaka in Zambia. And so the idea being that these units have relatively homogeneous layouts of buildings within them. That was the aim, at least. And so in terms of actually creating this index, then there's been a range of guidelines which typically consider 2 meters or 6 feet to be a pretty standard measure for social distancing. So in terms of the input data for calculating this index, we use building footprint polygons and population count rasters. And the building footprint polygons look something like this. This is just a sample area. And so you've got a polygon for each building. And these were produced by Ecopia using imagery from Maxar for 51 countries in sub-Saharan Africa. And most of the imagery within urban areas is about from 2018 or 2019, but there is some older imagery in there as well. In terms of the development of the index, then the variable around the built environment was calculated based on the proportion of the area occupied by buildings and just split down into 10% into classes of 10%, with values ranging from 0 to 10. And similarly, the population variable also varied from 0 to 10, but this was calculated, classified based on the theoretical maximum possible population density with that would be achievable with different distancing parameters. And so it's an idealized model that we used of perfect spacing between people based on a hexagon tessellation, with 1 person per hexagon at the center of the, there's the hexagon centroid. And so these values varied also from 0 up to 10. And then to calculate the index value itself, then the 2 variables were combined, just calculating a mean value of the 2, and the overall index value ranges from 0 to 10, with 0 being a measure of there being no building footprints and no estimated population for a location, 1 being an area where less than 10% of the area is occupied by buildings, and a population density of less than 2,004 people per kilometre squared. And a value of 10 is generally an area where 90% of the of an area is occupied by building footprints, and population density is greater than this value. And so the initial results, we have mapped outputs for urban areas within 10 countries, which are listed on the slides here and shown on the right. And this covered 170 urban areas with a total of 23,000 kilometres squared, and index values calculated for 166,000 spatial units. Now looking specifically at Zambia, we had mapped outputs for 38 urban areas in Zambia, and these are just ranked on this. So this graph just shows the proportion of the units that are in each class. So the maximum class value for Zambia was 8. And these are just ranked. So the highest proportion of a class in with a value of between 6 and 8 is just on the left, decreasing from left to right. So we have Lusaka, the capital, right on the left, and then Kitwe, which is another city in the Commonwealth, had the second highest proportion of spatial units that fell within these high class values. And we'll have a look at these examples now. So first of all, looking at Lusaka, we can see how we have the population density score here at the top in purple, and then at the bottom in green, we have the built score. And combining these into this index value, we get this map showing how these index values vary across Lusaka. You can see areas of blue, dark blue throughout, but particularly areas down here in the south, up here. Thank you. And then pockets distributed across the city. So looking specifically at this one area, we can see the two data inputs on the left. We can see satellite imagery on the top right. And then we can see how you can have areas where the index values are very low. So we have a value of 1 here, in very close proximity to higher index values. So here we have values of 6.5, and you see corresponding to this area of dense built structures here on the map. And so these can be useful in really just highlighting the locations where it's likely to be difficult for populations to socially distance. And this can have implications in terms of considering policies and need for adjustment of public health measures, like in these locations. So looking at just quickly at a second example, this is for Kitwe in the Copperbelt region of Lusaka, of Zambia. Once again, showing population density and the built score, and then combining these into the index value. And you can see here, interestingly, a bit of a different pattern from what we see from Lusaka, but we can see there's a particular area down in the south here where there seems to be an area with much higher values. And if we zoom in and look at this, we can see there's these two areas of very dense housing, and these reflect the higher index values. So in conclusion, we've produced mapped outputs for urban areas in 10 countries already. We've got work ongoing for producing data sets for a further 40 countries, so there'll be 50 countries in sub-Saharan Africa in total. And the data are all freely available to download from the website link there from the World Open Population Repository. And then in terms of next steps and further work, as I just said on the previous slide, then there's ongoing work to increase the number of countries covered by this data set, and they will cover an additional 40 countries. We have ongoing work at the moment in sharing these data sets within country stakeholders and integrating these into further analysis and mapped outputs. And then we're considering other applications outside a direct COVID use case here. And there's potential as well we'd like to investigate around development of a gridded data set and applying this index in a more developed country context as well. So this work just was, as I said, was part of the Grid 3 project with funding from the Bill and Melinda Gates Foundation and the Foreign Commonwealth and Development Office, with the other project partners listed there. Thank you. Does anyone have any questions?
Yeah, so when you devised your index, I saw you had like the two main domains, your two main variables. In an idealized world where we can get whatever data access we want, would there be like any sort of data sources that you'd like to add in, such as like footfall, for example?
Yeah, so that's one limitation of the approach, that it's just based on residential population. So typically population location based on census, which is typically residential. But yes, it doesn't do a particularly good job of identifying locations where you can get high footfall during the day. So in locations where transport hubs, markets, things like that. So yeah, being able to incorporate data around footfall or population movement, and potentially looking at this if it varies temporally during the day, that would be that would really be something interesting to look at.
Got a question that says, apologies, can you repeat how you used OSM to create those smaller units?
Yeah, I didn't go into too much detail there. I knew I was running a little bit short on time. Let me just, so essentially the list of the features here, these were the tags that we used from OSM to extract all the different features. And then we essentially converted, so they were all line or polygon features, and then we converted all the features to be polygons. So essentially combining both line and polygon features to create polygons. So essentially, so you'd have things like roads and paths here, which would generally be line features, and other features like a park or golf course would probably be like a boundary of a polygon. And then we just intersected them together to create polygons. I can't remember it's scripted within ArcPy, and I can't remember the exact tool we used. It's something to polygon, but I'm happy to follow up if someone's got a specific question to go through that in more detail.
Well, how reliable are the population density estimates? Could this bias the results?
Yeah, I mean, this is a limitation of the approach, is that, and also particularly at this point in time. So the majority of the population estimates that we've used are based on census data, with a few exceptions. Zambia's not, but most of the other countries are census projections. So if we're lucky, that's 2010 round projected forward. But in some cases, then the census estimates are going to be considerably older. And so, yes, in locations, particularly if there has been urban expansion within a city in a particular area, and that compared to when the last census was, then that's likely to introduce some bias, with the density likely to be underestimated. Although the advantage of using both the building footprints and the gridded population data set is that we do, although the population estimates may have some spatial bias because of urban expansion, for example, with the building footprints being from a more recent time period, then that should reduce that bias to some degree, but it will still be there.